Okay, so Bismillahirrahmanirrahim. Welcome to this week's class of digital communication. This is your course instructor Dr. Naveed Mufti. In this part of the lecture, we will be looking at the correlation receiver. Once again, you have to be careful that there are concepts and theoretical knowledge involved in this part of the course. So you are encouraged to write and make notes as you listen through these lectures. So last week, we looked at noise and communication systems, signals and noise. Within that topic, we looked at error performance degradation in communication systems, demodulation and detection as the two main steps in digital receiver, a vector view of signals and noise to have a better understanding of how noise affects signal vectors. Then we discussed the basic SNR parameter for digital communication systems, which is a normalized version of SNR known as EB by N0. And then we looked at the detection of binary signals and Gaussian noise. And in the end, we discussed error probability indicated by PB. And finally, we discussed the match filter. So in this week, we will start off by looking at the correlation realization of the match filter. And once we do that, then we'll be looking at how we can optimize the error performance. And then we will look at the design of the correlation receiver. And finally, some discussion on the binary decision threshold. So many of these topics are a reinforcement or slight extension to the topics we discussed in the last week. So the learning outcomes for this part of the course are as follows. The student should be able to first display an understanding that the match filter or the correlator is the most optimum choice for maximizing our signal to noise ratio and minimizing our probability of error. Secondly, the student should be able to choose the best threshold for detection based on the detection discussion we have done last week and this week. And they should be able to demonstrate an understanding of the working of the correlation receiver. So these are the main learning outcomes. So a quick recap of the match filter. As we have discussed last week, the match filter, it provides the maximum signal to noise ratio at its output for a given transmitted symbol waveform. And the expression that we derived was that the maximum value of signal to noise ratio at the sampling time capital T is less than or equal to 2E by N0. And this inequality is equal when the transfer function of the system is of this form, as I have shown here. This was also shown last week, and the transfer function is of this form here. And when we look at it in time domain, this basically means that the impulse response of the channel is like this. Within the signaling interval. So it means that the impulse response of a filter that produces maximum output SNR is basically the scaled version of the message signal, getting multiplied by a constant K and delayed by the symbol time duration capital T, like this. We also simplified it even further by saying that the channel's impulse response is basically just a delayed version of the message signal. So here it is graphically explained. For example, if S of t represents your signal waveform, so its negative will be its mirror image about y-axis, so it will look like this. And then if we introduce a delay of symbol time duration capital T, so this will basically show a shift and it will look like this. So this graphically and mathematically it is written as this. This is the wanted impulse response of the matched filter. So that is what we want, a matched filter. Now we come over to the correlation realization of the match filter. So first of all, the figures that we have seen on the previous slide, they illustrate the matched filter's basic property, that the impulse response of the filter is a delayed version of the mirror image of the signal waveform, as we have discussed. So the output Z of t, as indicated here, this output, the output Z of t of a causal filter, can be described in the time domain as the convolution of a received input waveform R of t with the impulse response of the filter. So that is how we can define Z of t. You've studied signal systems, so you know that that is how we can represent the output coming out after the matched filter. Okay, so basically this becomes the equation, and the convolution that can be written as an integral. So in this equation, if we substitute h of t from the previous slide, the expression from the previous slide, and if we substitute that into h of t minus tau, and we assume that the constant k is unity, okay, so after this substitution, this equation, it changes into this, and when we open the brackets, then it becomes this, and when t is capital T, yes, we can write this expression as this. So basically they both cancel, and this is what we are left with. So what is this thing? Yeah, so in all this expression in derivation, just remember that Z of t, it represents the output of the causal filter. So this, the final expression we have, Z of capital T, that is the product integration of the received signal with the replica of the transmitted waveform over one symbol interval. This is what is called correlation. So this is basically the correlation of R of t with S of t. So this is basically the start of the correlation realization of the match filter. We continue our discussion of the correlation realization of the match filter. So let us consider that the received signal R of t is correlated with each prototype signal Si of t, where I is equal to 1, 2 up to m. So if our signal can be any one of the m signal waveforms, our received signal is basically correlated with each prototype signal. And that we do by using a collection or a bank of m correlators. And then the signal Si of t, whose product integration or correlation with R of t yields the maximum output Zi of t, that is the one, that is the signal that has the best match with R of t as compared to all the other prototype waveforms. So one will have the best or the maximum value, and that is the one that is selected by the receiver, assuming that it was the one that was transmitted. So it performs a correlation with all the prototypes, and then based on the maximum value of the correlation numerical value, it selects the one with the maximum value and assumes that that was the one that was transmitted. So it is similar to that minimum distance concept that we studied when we looked at signals in the vector space. And this is the background that is used for optimum detection of signals. We already have that background, you have that graphical picture in your minds, and mathematically that is how it is being done. So as I said, we have to optimize the error performance. So to optimize or minimize the probability of error in the context of an AWGN channel and the receiver shown here in this figure, we need to select the optimum receiving filter in step 1. We need to select an optimum receiving filter here and an optimum decision threshold here. So here I am giving you two different examples for comparison. So the two things we need to do is to decide an optimum decision threshold in step 2. Yes. And for binary case, we've already discussed that. And then we have to also select the optimum receiving filter in step 1. So we have to choose the match filter because that maximizes SNR. So basically what we need to do is to maximize the difference between the possible signal outputs. Okay, so when we maximize their difference, basically we maximize our SNR or our capability against noise. So which means maximizing A1 minus A2, which means maximizing the difference between the values of A1 and A2. So that means the further apart A1 and A2 are, the greater is the difference between them and greater is the SNR. So previously we discussed that the match filter was described as the one that maximizes the output signal to noise ratio for a given known signal. Here we continued that development for binary signaling, where we view the optimum filter as the one that maximizes the difference between two possible signal outputs. Okay, so what you have to remember is that now we are trying to maximize the difference between the two possible outputs. And now if you look at these two figures that I have shown, you've got this choice. So let's say this is A1 and this is A2, or you've got this choice. So which has greater distance? What do you think? The distance between these two is greater, or the distance between these two is greater? So wherever the difference is greater, we will have a better or a higher value of SNR as compared to the other case. So clearly it shows that this case is better. Now what is this case? This is the case for orthogonal signals, and this is the case for antipodal signals. So if noise is the only degradation, we know that our received signal is basically our transmitted waveform combined with noise. So given this R of t, our detection process has two steps, as we know, this and this. These are the two steps. In step 1, our received waveform is basically reduced to Z of capital T here. So in this step we are transforming a waveform into a point in decision space. And in step 2, the simple decision is being made, which is based on comparing our sample value, Z of capital T, to a threshold. And basically what it translates into is that in which decision region the point is located. So with this background, for the detector to be optimized, it is necessary to do certain things. If we want to optimize it, we have to optimize this step. We optimize the waveform to sample transformation, and we use a match filter or a correlator in step 1 for that. And then we optimize the decision criterion in step 2. So by optimizing both steps, basically we optimize our receiver design, or we optimize our correlation receiver. So from previous knowledge, we know that the match filter, it provides maximum SNR at what time? It provides maximum SNR at the filter output at the time t is equal to capital T. That's what we remember. And then we have, as we have discussed in the previous slides, correlator is basically a realization of the match filter. So as we know that to correlate means to match, so we can define a correlation receiver as consisting of M correlators, and it transforms the received waveform R of t to a sequence of M numbers or correlator outputs, and then the correlators, they attempt to match the incoming received signal R of t with each of the candidate prototype waveforms, and these waveforms are known a priori to receiver. So basically this is the background of the correlation receiver. And the correlation receiver, if we look at it graphically, this discussion on this slide, if we look at it graphically, basically each correlator output is characterized by this equation. So we've got m correlators, phi goes from 1 to m, and there is an output corresponding to each correlator, and that output is governed by this equation here. That is the equation we derived previously as well. So as you can see, the I keeps changing, so R of t is basically correlated with every prototype waveform, so there is an answer to every of this equation, and in the end we have few values to compare, and the decision rule is that we will choose a waveform as I of t that matches best, in simple words, or we can say the one which has the highest correlation with R of t, or the one whose index corresponds to the maximum value of Zi of t. So this is what it looks like. So the received signal is then first multiplied with the reference signals. So we have all the reference signals here known to the receiver a priori, and once we multiply our received signal with the reference signal, then we integrate it. So this implementation is represented by this equation, and then that's the output. So that's the output for the first correlator, similarly second, third, fourth, that's the output for the mth correlator. And once we have all the outputs, we have a decision stage where the comparator, it selects the Si of t with the maximum value of Zi of t. So, and then decides in its favor that that was the waveform which was transmitted. So considering that case for a binary detection receiver, so for binary, our m correlators where m is equal to 2, so we will have basically two reference signals, S1 of t for 1, S2 of t for 0, and whatever signal we are receiving, that will be first multiplied, the product, and then integrated. So we will have two values to compare, Z1 of t and Z2 of t. So we will compare them, and then the correlator or the decision stage will decide in the favor of one of them. So either we can have, for binary, either we can have a receiver design in that way, which involves having two correlators. This is one and this is the other. Or we can have our correlation receiver configured as a single matched filter or a product integrator. So if that's the case, when we are using a single correlator or a product integrator, then we need to do is that instead of the specific individual signals acting as reference, the different signal acts as our reference, like different signals. So, and then our received signal is multiplied by the different signal, and then a decision is made on whether that is greater than the threshold or less than the threshold. So the difference between these two configurations is obviously that here two match filters or product integrators are used. Here one match filter or product integrator is used. And the end result is the same. Ultimately, we have to make a decision, and that decision will either go in favor of S1 or in favor of S2. So these are two different ways of implementing the correlation receiver for binary detection. So coming over to the discussion on the binary decision threshold. So we have looked at this curve previously as well. So this figure illustrates two conditional probability density functions, probability of Z given S1 and probability of Z given S2, with mean values of A1 and A2 respectively. And these PDFs, they are also called the likelihood of S1, this one is likelihood of S1, and the likelihood of S2. So they have been previously discussed, and we've also discussed their mathematical equations. So this is the equation for this PDF, and this is the equation for this PDF, and you can see that their shapes are very similar, symmetric, but they are different in their mean values, as shown here in this equation as well. and then we are looking at our decision making criterion. So here in these equations, once again, this sigma naught represents the standard deviation and its square that represents the noise variance, and this rightmost likelihood, it illustrates the probability density of the detector output z of t given that S1 was transmitted, and this likelihood function, it illustrates the PDF of z of t given that S2 was transmitted, and the abscissa, this x-axis here, that represents a full range of possible sample output values from the correlation receiver. So with reference to optimizing the binary decision threshold for deciding in which region a received signal is located, so we discussed previously that the minimum error criterion for equally likely binary signals, if it is corrupted by Gaussian noise, the optimum threshold value can be given by this equation, where A1 here is the signal component of z of t when S1 is transmitted, and A2 is the signal component of z of t when S2 is transmitted. So the threshold level gamma naught, which is represented by the mean or the average of the values of A1 and A2, that becomes the optimum threshold, which will minimize the probability of making an error or an incorrect decision, given that the signals are equally likely and the likelihood curves are also symmetric. So what was the decision rule? Based on this, what decision rule we can conclude? It states that hypothesis H1 should be selected, or in other words, deciding that signal S1 of t was sent if z of t is greater than gamma naught. And hypothesis H2 should be selected, which is equivalent to saying that S2 was transmitted if z of t is less than gamma naught. If z of t is equal to gamma naught, then the decision can be an arbitrary one and it can go in any symbol's favor. So if we have, in this case, if we have equal energy and equally likely antipodal signals, antipodal with the signals are in amplitude wise they are the same, but they have 180 degrees phase difference. So for antipodal signals, S1 of t is basically the negative of S2 of t, which means that A1 is the negative of A2. Then this optimum threshold rule, we apply those values here. If we put those values here, then that is what we get. We are basically comparing to the value of 0. So in this case, we will decide S1 of t if Z1 of t is basically greater than Z2 of t, and we will decide in favor of S2 of t if Z2 of t is greater than Z1 of t. So this basically ends the first part of this week's lecture, and now we will consider a numerical example. Okay, so now we come to the numerical question that we talked about. So you consider a binary communication system that can transmit signals S1 of t or S2 of t, and you know that your sampler will give you an output Z of capital T, which will have a signal component and a noise component. So your Z of capital T will either have A1 plus N naught or A2 plus N naught, and since it is a binary antipodal system that has been given to you, so you have to decide with values of for A1 and A2. You can assume unity magnitude, and you assume that the noise that is getting into the system, it has a uniform power spectral density. So these are the conditions that have been given to you about the system. In addition, you have been told the shape of the probability distribution. So the likelihood of S1, you have been informed that it has this value, so it is basically equal to 1 by 2 for a certain range of z, and it has a value of 0 otherwise. So it's a good idea to plot it actually, to see it graphically. So if you have z on the x-axis, try to plot this conditional PDF and see what it looks like. So you have z on the x-axis and probability on the y-axis, and you must have a curve based on this equation. You should be able to do that. And secondly, that is the likelihood of S1. You're also given the likelihood of S2. So that is equal to 1 by 2 for a certain range of z, and it is 0 otherwise. So this is the further information you are given, and you have to find the probability of bit error for the case when you have equally likely signaling, first thing, and you have symmetric probability density functions. So based on that, you have to use the optimum threshold or this equation for probability of bit error, and you can use the other equation as well. So you can use either of the likelihood functions to determine the probability of error. So because they are equally likely and because the PDFs are symmetric, so you can use this equation. Yes, and you have been given the values of A1 and A2. So based on that information, if you try to calculate the value of gamma naught by using this, so you can calculate the value of gamma naught. So since you have been given the values, first let us try to plot. I'll do a very rough plot of the likelihood functions. So if this is z, yes, so plotting this likelihood of S1. So if this is minus 0.2, and somewhere here is 1.8. So between this range, when z is from minus 0.2 to 1.8, the value of the probability density function is half. So let us say this is half. Okay, so on the y-axis is probability, and on the x-axis is the value of the random variable. So it's a constant, it's equal to 0.5 for this range. So basically this is what it will look like. So this curve here is basically the likelihood of S1, probability of Z given S1. That's the first thing you need to do, as I told you. Visualize it. And then for the second one, let me choose a different color of the pen. So for the second likelihood, the likelihood of S2. So for this range from minus 1.8 to 0.2. So let's say this is minus 1.8. And here it is 0.2 here. 0.2. So it is defined for within this range, and within this range the value is 1 by 2 once again. So if I try to plot it, show it graphically, this is what it looks like. So this one here, that is the likelihood of S2, or the conditional PDF probability of Z given S2. So these are my two answers, or the two PDFs, as you can see on the screen. So these are my two PDFs. Okay, and you have been given some additional information. For example, you were given the values of A1 and A2. A1 and A2 as 1 and -1. So let's say these are the values of A1 and A2. So this will be A2 and this value here will be A1. Okay, so you have this information and you can calculate the value of gamma naught, and the value of gamma naught, it comes out to be based on these values of A1 and A2. The value of gamma naught as per this equation, it comes out to be 0. So on this graph 0, what color should I choose? Let me choose blue. This is your gamma naught here, 0. This is your gamma naught. Okay. So that is value for your gamma naught. So based on this information, now you know the value of gamma naught. So if you put the value of gamma naught in this integral here, so basically this integral, the lower limit becomes 0 and the upper limit becomes infinity, and that is P of Z of given as 2 and dz. Now looking at this figure, which likelihood curve are you considering based on this equation? You are considering the green one. Okay, considering the green one. And for calculating the probability of error, the starting limit of the integral is gamma naught, which is 0. So basically on this likelihood PDF, you have to start the integral from 0, from this point here, and you need to go up to infinity. But the reality is that it does not exist up till infinity. It is only defined till point 2. So in order to simplify your work, you can change the upper limit from infinity to 0.2. So the lower limit is 0, the upper limit will become 0.2. And within this range, when the value of Z is between 0 to 0.2, what is the value of the likelihood function? It is constant. What is the value? 1 by 2. So here you don't need a long mathematical expression because you have been given a constant value which is 1 by 2. So that is what you can use. So you can actually put all the values in the integration and you can solve it numerically. So basically if I substitute the values here, so I have 0, I have 0.2, and this value here, this is basically 0.5. So when I integrate and calculate, the answer I get is 0.1. So 0.1 is my answer. So that is the probability of error. I can also use the other equation using the other likelihood curve to calculate the value of probability of bit error. And in that case, the limit will be from minus infinity to gamma naught. So effectively, it will be from minus 0.2 to 0. And then I use the same. Its value will be 0.5, and when I put the values in, I get the same answer. I get 0.1. So as we discussed, that we can get the probability of bit error from any of these equations, and that will give us the same answer. So this is how you solve them numerically.